In this video, we'll be discussing torque and work. In linear motion, forces do work and change kinetic energy. In rotational motion, torque does work and changes rotational kinetic energy. We're going to connect torque, work, and energy in rotational systems and solve some physics problems that mix these ideas together. So, some non-negotiables for this topic are the topic of rotational work, which is done when torque causes an object to rotate through an angle. So W is equal to R times theta. So some conditions for this is torque must be constant and the angle must be in radians. This is the rotational analog of work is equal to force times the displacement. Now, what you need to know is that torque can do work without translating an object. Work and work depends on angular displacement, not time, unlike translational. Forces through the axis do zero rotational work, and also static friction can do zero work even when enabling rotation. So let's look at some examples that exemplify these ideas. So we have number 1, a constant torque of 5 newtons times meters acts on a disk. The disk rotates through 3 pi radians. Find the work done by the torque. So we know that work is equal to the radius times the angle theta. So work is going to be 5 times 3 pi. So work will just be 5 pi joules. And remember that the angle must be in radians when you substitute it in here, Let's continue on with the second example. A solid disk, mass M, radius r, starts from rest and reaches an angular speed of angular velocity omega. Find the net work done on the disk. So we have this radius and it has a mass. So we know that initially it's going to have 0 kinetic energy, and then finally it's going to have a level of rotational energy. So, and we also know that for a solid disk, we know the moment of inertia is just 1/2 mr squared. So then if we substitute that into here, we just get that kf is going to be equal to 1/2 times 1/2 mr squared, and that is just going to give us 1/4 mr squared w squared, omega squared, And now we can apply the work energy theorem, And by doing this, we know that work net done is equal to the change in the rotational kinetic energy. So the work is going to equal to 1 over 4 mr squared times omega squared, since the change is just kf minus k initial, and the k initial, this was just 0. Now let's move on to another problem. A solid sphere rolls down a hill from height h without slipping. Find the speed at the bottom. Let's make a triangle. Now you have a sphere and it rolls down the hill and it is height h and there is no slipping, and you want to find VF. So we know that we can use energy conservation. So by using this, we know that the initial energy is going to be equal to U, which is equal to potential energy, which is the only form of energy that's up there, which is equal to mgh. And then we know that finally all that potential energy, once it reaches the bottom, has been converted into kinetic energy. So we know the formula for that is 1/2 mv squared plus 1/2 inertia times angular velocity squared, because it had to roll. And because it had to roll, some of the translational energy became rotational energy because of the rolling. So now we can use the rolling condition, which is that omega is equal to v over r. And we know that for a solid sphere, we know that the moment of inertia is 1/2 2 over 5 mr squared. And because we know this, we can now substitute that in for the I that we had up here. So by doing that, we just have that the final, that EF is going to be, we can write out that E initial is equal to EF. Therefore, we can plug in both sides, mgh, and 1/2 mv squared plus 1/2 times 2 over 5 mr squared. And we can also multiply, instead of omega, we have here the rolling condition, right? So we got this rolling condition. Therefore, one second, and this is just going to be v over r squared. Now, if we simplify this algebra down, we have 1/2 mv squared plus 1 over 5 mv squared. And this is from 2, that 2 cancels out. And then the r squared is there. So then the r squared cancels out with that. And then you just have this v squared. Let's make that a little bit more obvious. So that's just mgh. And then here, if we just combine these two fractions, well, we know that 1/2 can also be written, well, we have 1 over 5 and 1/2. So how can we get a common denominator? Well, we have 1/2 is basically the same thing as 5 over 10, and 1 over 5 is basically the same thing as 2 over 10. So that's just 7 over 10. So that's going to be 7 over 10 mv squared. But what we want is we just want what the velocity is. So we're going to have to divide that by 1 over m, and we have to multiply this by 10 over 7. So doing the same thing to the other side, we have 10 over 7, and these are going to cancel over here. Now we're just going to have that, and we also want to take the root of both sides because we want to cancel out that. And then we are just left with v is equal to the root of 10gh divided by v as our final speed, as our VF. So from this, we can deduce that static friction does no work but allows energy transfer into rotation. So essentially, some takeaways that we want to have are that torque, it does rotational work. Rotational work changes rotational kinetic energy. You always want to use radians, and rolling problems use translational and rotational kinetic energy. Static friction, this is a big one. Static friction often does no work. And also use energy methods to avoid force and torque algebra. Alright, thanks for watching.